Hello, I'm Hongjin Huang. Welcome to this video. I'm going to give a brief summary on our work of constraining both baryonic physics and cosmology utilizing small-scale cosmic shear of DSY1 data. The figure here shows the cosmic shear correlation function of DSY1. The gray bands highlight the angular scales that were excluded in the original Y1 analysis due to modeling challenges at small scale. Here we perform a reanalysis on the Y1 3x2 point data with the inclusion of these small-scale cosmic shear data points. And for the observables of galaxy-galaxy lensing and galaxy clustering, we simply set their scale class to be the same as in Y1. In other words, we only extend cosmic shear to small scale while using the large scale data points of galaxy-galaxy lensing and galaxy clustering to provide information. The goal of this project is to see if we can, firstly, reach better cosmology constraints with the inclusion of small-scale information while properly marginalizing over the dominant uncertainties caused by baryon, and second, place constraints on the feature of baryonic effect. Figure 1 of the paper shows the ratio of power spectrum derived from a total of 11 hydrodynamical scenarios with respect to their dark matter-only counterparts, setting at the same initial condition. As shown, baryons could induce a level of 10 to 30% uncertainties in the power spectrum towards small scale compared with the dark matter-only based model. And the right panel here shows the baryon-contaminated cosmic shear observables, psi plus and psi minus, derived based on these hydrodynamical scenarios. Utilizing the information provided from hydro simulations, we perform principal component analysis on the quantity of weighted difference vectors in the observable space, and identify a set of PC modes to span the space of uncertainties opened by baryons. The difference here is defined as the difference between the hydro and the dark matter-only based model vectors, and the weighting factor here is related to the square root of covariance matrix. By applying the weight when performing PCA, it would boost the efficiency of the first few PC modes in accounting for data points, not only with larger baryonic effect, but also with smaller errors, which turns out to be more efficient in the overall performance of this method. After reorganizing the above equation a bit, we can then have a baryon model generator with all the cosmological dependence going through the dark matter only based theory model, and the second term would then serve as a higher order correction on top of that. Figure 2 provides a visualization on the behavior of the first three PC modes. We will use them to model the baryonic features of the cosmic shear observables showing in the left panel. And as you can see, the first PC modes mainly capture the suppression of power provided by baryons. So, with the functional form specified by the principal component, the PC amplitudes can then be used to quantify the feature of baryons. Here shows the representative Q1 and Q2 values for the hydrosims listed here. We have validated that marginalizing over one PC mode is sufficient given the Y1 data quality to safely marginalizing over baryons down to 2.5 arc-minutes of cosmic shear, and we adopt two levels of priors on the baryonic parameter Q1, one being non-informative, which serves as our baseline analysis, the other being in the range as highlighted. We use the illustrated scenario as a standard to set the upper bound on the strength of feedback, because it is known by the community that Illustrates has an overly strong radial mode AGN feedback subgrid physical model. Table 1 provides a list of parameters when modeling the 3x2 point observables, as well as the prior information adopted. We adopt mostly the same priors as in DSY1, except for the neutrino prior. In the original Y1 analysis, a Y non-informative prior is adopted. We change the upper bound based on the constraint of Planck and BAO, and the reason for adopting an informative prior is to alleviate the parameter projection effect caused by the asymmetry range of neutrino prior and the fact that the Y1 data is not constraining neutrino. Finally, here comes our baseline cosmology result. By baseline, I mean marginalizing over a wide flat prior of the Baryonic parameter Q1. The yellow contours indicate the result when the conservative Y1 scale cut is applied, and the blue contours show the result after marginalizing over baryon uncertainty with the Y Q1 prior. We see almost no gain in cosmology information given the range of uncertainties opened by baryon. And here is the best fitted cosmological parameters under the lambda CDM framework. But with the adoption of informative baryon prior, shown in the shady gray contours, we can reach about 20% improvement in the marginal 1D SA constraint. Regarding on the baryon constraint, here is the posterior distribution of the baryonic parameter Q1. The thinner lines at the background are the representative Q1 values for various hydrodynamical scenarios. We are able to rule out the most extreme baryonic scenarios at 2 sigma level with DS data alone. We further try to push the limit of baryon constraints by narrowing the allowed range of cosmology. We set the cosmological prior information based on the external data sets of Planck polarization plus BAO, and the red contours show the combined posterior distribution on SA and Q1 plane. As also revealed here, there is an apparent degeneracy between cosmology and the baryon parameter Q1. So after adopting an informative cosmology prior, we can further improve the Q1 constraint by about 40%. Now the most extreme baryonic scenario is further ruled out at 2.8 sigma level. And generally speaking, the resulting Q1 posterior distributions indicate a preference for moderate to weak baryonic feedback. Here in figure 16, we convert the best fit and the 1 sigma confidence interval of Q1 constraints back into the space of cosmic shear observables. This figure provides a visualization on the suppression feature caused by baryonic effect from the Y1 data. Although the 1 sigma error bands are still wide here, we anticipate the upcoming Y3 data to provide more interesting results for the future. Finally, here is the summary slide for the major content of this paper. Please check our work on arXiv for more detail with the link below, and thanks for watching.